Hi, in this video I'm going to demonstrate how I use automated testing to validate the design of relatively complex schematics in the Proteus Professional Design Suite that I use for my MegaWang video hardware. When I'm looking at relatively complicated schematics like this page, for example, which is actually the scaled sprites scanline output phase, and it gets the data from the scaled sprites calculation schematic, which is yet another complicated schematic, and the rest of the boards are relatively large and complex. The ICs are not even populated on this. There are some placed already, but I tend to rely on manual automated push and shove placement from the design tool because I don't want to spend time manually placing hundreds of ICs. So all of these boards and all of the schematics for these boards can be tested with automated testing software, which I've written. Being a software engineer as well as dabbling in hardware, I understand the benefits of repeatable and reliable automated testing because I don't want to have to manually go through and validate these schematics when I make changes. I want to make sure that changes that I am making to these schematics do not break existing functionality. I want to make sure that I do not get any regressions in the functionality. So when I'm normally editing these schematics, I normally run a quick manual sanity check, which is true, because I want to make sure that there are no logic contentions or anything like that, and I just quickly look at some expected output that I'm wanting to see. So I've just started the simulation here, and it's compiling the netlist now. Because I'm recording, everything is a lot slower than normal, but with this MegaWang video hardware specifically, I had to create this output model which would actually simulate the output based on vertical sync, horizontal sync, and then the three RGB component inputs. These are digital inputs. Now, of course, I can use the Proteus design suite debug tools such as the logic analyzer, and sometimes I do. You can see here in the schematic that some logic analyzers are connected to the data bus, the address bus, and so on and so forth. And if I'm looking at trying to debug timing issues, I can certainly use these. However, normally when I'm looking at visual output, I don't have the logic analyzers active. Also, if I pause the simulation, then I have the option of actually looking at memory contents. So say, for example, if I wanted to look at the memory contents for U71, then I can do. At the moment it's nice and empty. But what this is doing is that it's actually using the input data generators here. So this is an input data generator. These other ones tend to be disabled in the simulation because only this one is active in the simulation currently. And this actually takes an input test data file. So the input test data file looks like this. It describes the input, the 32 bits on the input data lines, and how it should output these 32 bits. So we have the address bus, the 16-bit address bus, plus the 8-bit extended address bus, and then the 8 bits here for the data bus. And all of these values can wait for the internal horizontal and vertical position, and also the feedback. And then it will output. And then it will output the signals to the video hardware, and this can add values or write values into RAMs. It can update the palette entries, for example, and then the video hardware will actually render. So this input test data file here can include other files, or it can output data directly, and we can recursively construct quite complex test data that I want to test, but what this does is basically it sets up a whole bunch of stuff. So the first stuff it does is that it does some debug pixel timing, it debug vector tests, which is what it's doing at the moment. It's actually rendering some debug vectors, and then it goes into the debug scale sprites, which is what we see here. So now it's debug drawing or rendering some scaled sprite information using some good known values. And this debug model here, actually for every complete frame, it writes the complete frames out to files. So I can see, for example, that it has just output this frame, which is debug frame number 7. If I go to the previous frame, it was blank. This is actually an animated GIF from one of the other tests that I was actually running. Blank frame, running the vector tests, different vector tests. This is another animated GIF from previous tests. So what I can do is that I can wait for this simulation to run, and then I can look through the screens and then see if everything looks okay. Or what I should be doing is that I should be relying on the automated testing. So I have the concept of being able to automate the testing by running this simulation using software test automation, and then capturing the output images, and then comparing the output images that are captured in the simulation with output images that I have previously validated as being correct. And this is my golden source test data. And so the automated test can actually validate between these two to check for differences, which is what this test case does. It creates some configuration file in the current directory to basically tell the simulation to exit after 0.36 seconds. It tells the simulation it should be using testdata.txt, and it says actually delete this configuration file after it starts the execution, so when I'm running it manually it doesn't pick up this override configuration. And then the test case scenario actually says to start the process with the bombjack Proteus project. So then it runs this Proteus design tool, and it loads the same file, and then it waits for the window, which is called this is a wildcard. This is actually a regex for looking for a window which has bombjack in it and the word Proteus in it, which is what we have here, bombjack and Proteus. Okay, and then it focuses the window, it expands the main menu, it expands the debug menu, it looks for the debug menu entry for run simulation with the F12 key, and it clicks that menu item, and then it waits for the window to close, because we've told the simulation to only run for 0.36 simulated seconds, not real-time seconds, because the simulation is very slow. So 0.36 simulated seconds, it then closes the window, and then it just has image validation syntax here, which, as I said, validates between the test data expected output with the actual output that was gained from the simulation. So this is an example of using a complete automated test to validate the correct expected behavior based on golden source data. This is an image test. It's like an image reconciliation test, if you like. I can also use other reconciliation syntax for other parts of the schematic that I've been working on as well. So if I go back to the APU project, and we'll wait for this to load. The APU project has, again, input data, and it actually captures output data. So the captured output data from APU execution captures all sorts of different things. It looks for the internal APU RAM, it looks for external RAM writes to a specific address range, and so on and so forth. So if I have a look here, then the output recorders will record in great detail the time and the delta time and what the current horizontal and vertical screen positions were, and what the data bytes were being output to, in this case, the APU data RAM. Okay, so we've got precise timing information and we've got precise written data. Now, I could manually check these files to make sure that they're correct, but there's not a lot of value in manually checking the files because it's repetitive work and it's very time consuming, and it's prone to human error, of course. So because it's just data in and expected data out, I can actually use the syntax here for validating the contents of the different output files. So I'm making sure that the APU, when it's running a particular test APU assembly file, when it's running specific APU code, basically, I can make sure that it is going to be outputting expected data in the form of this. Now, for this, I'm not too interested in the timing. I'm just making sure that the correct data is output on a specific bus. For this one, I'm expecting to see or expecting to validate certain timings between APU output internal bus writes, because I want to make sure that the APU bus contention logic is behaving correctly with the correct expected wait times between the writes. So I'm actually checking the delta write times here, or the deltas between the different writes for these memory addresses here. And again, for this kind of test scenario here, I'm actually looking at the expected output writes to the external memory bus for a specific memory range. And this specific memory range is actually captured by this test logic here. And this test logic here is basically the same memory bus decoding logic that I'm using in the video hardware. So it's using exactly the same parts with exactly the same timings. So I'm making sure that, at least for this memory range, which is actually the sprites memory range, I'm making sure that writes to the sprites memory range are actually would actually flow through to the video hardware correctly without needing to import the full video hardware schematic. And I can also do other tests. So if I go back to the test scenario, the test scenario here just basically goes through and tests all of these sprite range. But I can actually do other test scenarios as well. So I can tell the APU schematic to then run with the test APU data 2 and the test data APU 2, which, if I go back here, test data APU 2 txt, then this contains a whole bunch of extra stuff for expected memory writes in different situations with different timings and different bus contentions. And then I can make sure that with some expected output data, I can reconcile very complex output data with expected golden source data, which I know from my own knowledge of how it's meant to behave. This expected output data is then used to match against the simulated output data and then produce a reconciliation output file. Now, if this output reconciliation file contains nothing, then that means there are no reconciliation errors between the expected and the observed data. And I know that the schematic is probably behaving in the expected way, because the tests that are run, the APU code that is run for this, is actually quite comprehensive. It tests a lot of edge cases. And I'm doing another reconciliation here with the output sprite address range as well. So I'm checking that the full video hardware external bus range, and I'm also checking a specific internal video hardware, if you like, bus range as well for the sprite registers, just to make sure everything is working correctly. Now, all of these automated tests use some vaguely easy to understand syntax. So the syntax is basically creating different configuration files to alter how the simulation runs. So in this case, I'm telling it to exit the process after 0.5 seconds, for example. I'm telling it to use the test data to APU configuration file for the input data generator. And I'm also telling it to force flush any data which is written to the expected output, or the observed output simulation file, for example. Again, I'm telling it to run the Proteus design tool, and I'm automating actions within the windows. Now, of course, the Proteus design tool doesn't have a headless mode. It doesn't have command line interface to tell it to actually run a simulation for a certain amount of time, so I'm having to do it by automating its windows, which is, kind of fine, but I would actually prefer it if it had a headless mode that I could just tell it to run for a specific amount of time by command line, but such is life. C'est la vie. So yes, all of these test cases are building upon a very similar pattern with the Proteus design tool, because the Proteus design tool is actually running most of the simulation and outputting most of the data. I'm just using this to automate the Proteus design tool. So if I quit this, what I can do is that I can actually show you this running. So if I run, well, I could just run the whole suite. So that's what I'll do. Let's just have a look at this last one here. Oh yeah, this other feature file has just one test scenario. Again, it's just telling Proteus to run a specific project, and then again it's looking for expected data in the expected output data. So let's just run the whole suite. Now what this should do is that it should go through both of the APU test feature files, and then it should run the simple CPU test, and then it should run the user port interface schematic tests, and then it should run a good few frames of the MegaWang video hardware tests. So you can see here that I'm actually not doing anything. I'm going to move my mouse down here at the bottom of the screen here. I'm just going to leave my mouse nice and stationary. Completely hands-free operation. You can see it just opens the window, it activates a certain debug menu for starting the simulation. It could also do it by sending the F12 key, but I prefer to do it via the debug menu, which is how you're meant to do it if you don't use the keyboard shortcut. We can see here it's running. It's animating. We can see here that the simulated time is actually very slow, and that's because the simulation is slow, because the APU is a relatively complex schematic. So if I actually open up the DOS command line window, you can see where it's running. It's actually opening the second window now. It's again starting the simulation. It's again running the APU. If I go back to the DOS window, there you go. This is the debug output from the test scenario editor window. So we can see here that it's actually waiting for the window to close. This is waiting for the Proteus window to close. The Proteus window will automatically close once the configured time period has elapsed. We can see here that it's using the exit process after with 0.5, so we will expect this to finish its simulation run when this number here is greater than or equal to 0.5 seconds. The request for the feature debug.json file here is actually the web interface requesting the test run output, which is inside the JSON file. And the web interface then uses the test results to then colorize the lines for the test scenarios and the feature files. It's quite a useful feature because it highlights where the failing test scenario step is in red. It highlights it in red. I'm going to compress the time on the video for these sections, don't worry. The next test scenario is actually running the simple CPU, and the simple CPU is actually a very simple schematic. It simulates very quickly because it's such a small schematic. The simple CPU, I think, runs a very simple Fibonacci sequence with an instruction set of my own devising. This next test is running the user port to 24-bit address bus interface. Again, it's a relatively simple schematic, so it simulates very quickly. The video hardware, which is the BombJack project, the main BombJack project, actually comprises of about over 400 integrated circuits across all of the layers. So it's a normal sprites layer, a characters layer, a tiles layer. The characters are 8 by 8 pixels and the tiles are 16 by 16 pixels. And they have different screen sizes, virtual screen sizes which can scroll. Then there is a mode 7 layer. There is a scaled sprites 2 layer. There is also a vectors layer. There is the video combination layer, and then the video timing output layer as well. There's also a combinatory layer where 2 or more outputs. And there we go. And run. Okay, so I can see that actually this test case has indicated that there's a problem. And I think what happened was that probably because I'm recording, it's probably, it hasn't actually finished outputting all of the expected frames. I think probably just Proteus decided to crash at that particular point in time. Perhaps anyway, we can see what happens. So we can see here, if I click on this, we can see here that the APU test cases are all fine. Well, actually, what I can do is that I can go to the output folder. The target folder, and then I can look at Cucumber, and I can click on this, and then there we go. We can see here that there's just no expected output. So I think Proteus decided to crash before it was able to output frame 9 or frame 9, which is a bit of a shame, but anyway, such is life. But anyway, we can see that, let's go back to the output, sorry, whoops, there we go. We can see that actually most of the other scenarios worked fine. So Proteus crashing while I'm recording is not entirely unexpected, because my machine was running extremely slowly and this schematic is extremely complicated. But what we can see is that the first 8 or 9 rather, because it's 0 based, the first 9 output image files reconcile perfectly fine. There's no changes there whatsoever. It's just that the frame 9 and therefore the rest of the frames here up to 17 just don't exist. So that's kind of fine. But we can see here also that the colorization for the reconciliation works very nicely. So if I wanted to, I could demonstrate that the reconciliation does find data errors. So if I, instead of editing the simulation, what I can do is that I can edit the expected data. So I'm just going to put a 1 here, and then I'm just going to run this particular file. And then this is going to run, again, the test with the user port test case within theory. Yep. It's just running it now. Here we go. Run, stop. And then, there we go. This is what it looks like if I made an error either in the test case or in the simulation, and then I'd have to go through and actually hunt down why. So this is what you would see. You'd see a line in red here. Like that. But anyway, let's return the test case back to the correct value, and then if I run the file again, it will open the Proteus window again, it will run the simulation, and then hopefully won't crash, and then hopefully the test scenario will work again. Here we go. And there we go. So because this particular test case failed last time, I'm going to just run it again just to make sure. Let's just run this particular file. Just let it run and do its output stuff. Just zooming into this model here so we can actually see what's being rendered. Something interesting to look at while it is running the test. Actually, if I go to here, we can see that these are all mostly data output generators. This one is recording the horizontal and vertical and VBlank information, so I can actually use it in the APU later on. This one's recording. This one is just using a different data timing model for the use of what direct from the Commodore 64 rather than from an APU, for example. This is so I can test the video hardware with different write speeds. Because the video hardware can use the output from the APU, which is very fast, or it can use the output direct from the Commodore 64, which is actually a lot slower than the APU. If I remember rightly, the output from the Commodore 64, because the Commodore 64 is only 1 megahertz and the APU is about up to 12 megahertz, then the APU can output memory on every other cycle, effectively. So the APU can be, like 10, 20, sometimes 25 or 30 times faster than the Commodore 64 can update memory in the video hardware. The APU is cycle or pixel accurate for its memory write positions as well as it's rendering the screen. So yeah, that's why I created the APU, was to actually have a lot more accurate and faster video hardware writes. So I could have things like parallax scrolling, and I could update color raster bars in the background, for example, to have nice color graduation effects and things, or to multiplex sprites without any accuracy issues. Using the APU is a lot better than trying to use the Commodore 64. So this is outputting frame. Well, this says here that it's measured the last frame at 59.7 frames per second, and it's outputting 264 lines, which is what we kind of expect. It's basing that on the timing information it's getting from the VSync. Let's have a look. Yeah, see, this time it's got to frame 13, frame 14, which is a lot better. Let's just leave it now. Once it gets to the correct allotted time for the test case, whatever it was 0.36 simulated seconds once it gets to there, which is going to be very close now, another couple of frames perhaps. It will then quit. Because it's nearly 60 frames a second, it's actually 59.7, so each frame is actually 0.01675 seconds. So we can see that actually we're pretty close. It's creeping up, and the rendered raster position is creeping down the screen. So each frame, sometimes the test data will wait for a particular horizontal and vertical position before updating the sprite registers. We're just basically animating the data by updating the various different internal registers and palette entries and so on and so forth. So all of this is just generating output frames that we check for being correct later on. Here we go. This Proteus window should close quite soon now. We're getting up to the 0.36 seconds mark. There we go. Finish. Now it's doing a reconciliation of the images, and there we go. The test scenario has actually worked now. We can have a look at all of the debug output files for the APU. Oh, well, there's nothing being captured for the internal data. There we go. There's a lot of information being captured in the APU files specifically. So this is the benefit of using the behavior-driven development test framework to actually drive real applications and validate expected output behavior. Thank you for watching, and if you like my crazy electronics and software projects, then please do consider liking and subscribing to the channel, and please do contact me via my social media links if you want to ask me any questions about this kind of stuff. Thank you very much, and have a great day or a great night wherever you are.